Hey Derek.
Hey.
Hey, you're a pilot, right?
Yeah.
Well, I was thinking about the other day why people put spoilers on their cars, and it doesn't really make sense, so I figured it has to do with wind or something, so you might know.
Oh, I can talk to you about that.
Yeah, sure.
Oh, man, if only I had like a really sweet visual aid.
Yeah, that'd be kind of neat. Wow, that's pretty neat.
There you go, yeah. So, really what you're talking about is lift, in a sense. So, do you know a little bit about airplanes, a little bit do you know anything about lift?
A little bit. I know that the wind kind of travels faster on one side than the other.
Yeah, that's part of it. So, pilots often cite Newton's third law. For every action there's an equal and opposite reaction. So that'd be right here on the bottom part of the wing. Wind is forced downward, creating an equal and opposite force upward, kind of pushing the wing and the rest of the airplane up. They also cite Bernoulli's principle, which essentially says high velocity here, up on the upper part of the wing, creates lower pressure and also pulls the wing upward and the rest of the airplane up. But it's a little bit more complicated than that. So one of the things that I'd like to share with you is the lift equation, which looks a little complicated, but it's actually not. You don't have to memorize this or anything, but good thing to know, velocity is squared, so velocity becomes really important in the creation of lift. So the faster you go, the more potential for lift you have. You know the coefficient of lift, which is here. It's kind of an experimentally defined value. You have wing area is really important. So airplanes with bigger wings can create more lift. And then you have the density of air here, which also is important in the creation of lift.
And the density of air changes probably with temperature sometimes?
Temperature, yeah.
Or like
temperature,
humidity,
pressure. Yeah, and humidity as well. So we know if it's really humid air as pilots, or really hot, or both of those things, the wing surfaces are not going to they're not going to perform at the best of their ability. So, we have to run performance numbers prior to takeoff and all that. Yep. So NASA actually did a lot of study on lift, as you can imagine, and they came up with this idea called flow turning, which is really just a combination of Newton's third law, like I mentioned, and Bernoulli's principle, which kind of just says that air is acting like a fluid. So although it's molecular and has points, it really is flowing as if it were a fluid, flowing around the wing in a pattern that is similar to a fluid. So when we talk about lift, we're really talking about a force, one of the forces that are acting on the aircraft. And when you talk about force, you know that force is mass times acceleration, which is Newton's second law, F equals ma. And you can express that as mass, excuse me, is a change in velocity over a change in time. So if you were to change the velocity of the air, let's say you were pushing it down, basically changing the direction, which velocity has a direction, you'd be also changing the acceleration. So if there's a difference here, then you're changing the acceleration. So kind of creating a force. Because if this value is 0, that means acceleration is 0 and force is 0. But since we're pushing the air down, we're creating a force. So yeah, here you go. Changing velocity creates a net force on the specific body that's changing the velocity, which is of course the wing.
So that's how birds can fly without moving, like at the beach, relative to the ground. They can just kind of glide but not be moving because the wind is blowing at them.
In a way, yeah, because they are pushing wind, even though you don't see it. They're either pushing it behind them or straight down. Depends, of course, if it's a hummingbird or a seagull or whatever it is. But yeah. So here you go. This is a kind of a force diagram. So we have an inflowing force. This would be like your wind. Your relative wind is the term that we use in the aviation world, which means wind flowing kind of relative to the airplane and its surfaces. So it's coming in, it's hitting the wing is here, not pictured. It's outflowing at an angle that's down, at a specific deflection angle. So you can kind of see here, some of these lines kind of go down. And you note a deflection angle, which of course is downward, and then the resulting force is up. Yeah. So parts of the wing, you got the trailing edge, which is of course at the back end of the wing. You can't, I didn't say this earlier, but this is the cross section of the wing. So if you were to go to the very edge of the wing and look back at it, and like here would be the cockpit, and way out here you'd be standing away from the aircraft. The chord line, which is a reference line that we use often to figure out what angle of attack the relative wind is hitting the aircraft. So often
it looks like is it the same as the upflowing force, or is it? I guess it depends on where you are, but
yeah, it could be different, but we use the chord line to kind of determine how. So we've got relative wind coming in at some angle, so it would be like this-ish for this kind of flow here. Chord line up just a couple of degrees, and if it were up too far, we might stall the aircraft, basically make the wing inefficient and not working. And if it were too low with the relative wind, it would do a similar thing. It wouldn't be efficient.
Oh, so if you're flying upside down, you still need to do the same thing, but working against the shape of the wing?
Yeah.
Okay.
Yeah.
So you have to like really think about where your chord line is, or know your equipment or something like that.
Definitely.
Okay.
And that can get complicated.
So that's how that works. So the shape of the wing can be the same, but you have to like counter that.
Yeah.
So you probably can't go as fast, or
you
have to go faster. Or
you'd have to use other things like thrust and point the nose higher in order to deflect more air, because it would be like the shape of the wings really helping this move through the air and push wind down, creating a lift. But see, you can kind of see if this were upside down, it would not be automatically pushing wind down.
Yeah.
You'd have to really kind of take the chord line here and just push it all the way like this. Yeah. Anyway, that's getting into stuff that I don't know even a ton about, because I've only done a little, but there are three properties of air that are kind of interesting to think about, and they relate to how air, as on a macro level, flows around the surface of the wing. So there's an inertial effect, which pretty much is Newton's third law, or sorry about that. No, it's actually the first Newton's first law, which pretty much means an object's going to continue unless it's acted upon. Yeah, and otherwise it'll continue going. So air's got the same idea. So as it's moving through, it'll continue unless the wing, of course, pushes it down, or it kind of bends around the wing here, which we'll talk about. It also has a pressure effect going on. So if you were to take a pocket of air, inside that, the air's got a certain pressure. It's either pushing or pulling on the sides of a box that you put around the pocket of air. That's pressure. And it's also got a little bit of oscillation, which kind of creates pressure. So higher temperatures, maybe that pocket of air, there'll be a lot of oscillation, and so if you box that pocket of air up, it'd be pushing on that box a lot. And then, of course, viscosity, which is a really interesting point. Air molecules have a tendency to assume their neighbor's speed and direction. So you can notice on the top of the wing, it's almost illogical that the wind is following the top of the wing. It's doing that because of viscosity. Otherwise, it would, without viscosity, it might just continue away from the wing.
Oh, like how water follows a pipe and might defy gravity.
Yeah. And water has a viscosity principle as well.
Yeah.
So there are a lot of misinformation out there. One of them is the equal transit theory. You may have heard of this because it was widely used for a very long time. And I'm pointing it out because this picture is actually a little wrong. The top, we know, as noted here, there's a higher velocity, and down here is a lower velocity.
Mm-hmm.
The equal transit theory says lift is created because two air molecules meeting at the wing at the exact same time go up. One of them goes up, one of them goes down. This one travels a lot farther, and this one travels a lot less distance, and they meet at the back of the wing at the same time.
Mm-hmm.
It's not true. Some professor at Cambridge actually debunked that by essentially shooting jets of air, just like this, at the same time to hit the wing, and you could see the jet that's kind of left, the wind tunnel at the same time move a lot farther than the ones down here.
Wow.
Yeah.
So the velocity is even like higher than they thought originally, because it's going further like horizontally.
Oh yeah.
Yeah.
So they're not traveling. They're obviously traveling at
Yeah.
different velocities, but they're not traveling together. They're not connected in any way once they separate.
Because I've heard that with sailboats too. That's how that works. So that's interesting.
Yeah.
This is kind of like looking down on a sail.
Definitely.
Yeah.
Different. We might have all we need.
Okay, cool. Well, can I try putting the poster away then?
Oh yeah.
Okay. How did you just snap?
Yeah, just snap.
All right. Well, thanks, Derek.
Yeah.
I'll catch you later.
Sure, you too.